Beyond looking at a normal stress or a shear stress that can be applied to a rigid member, we also can consider the bulk modulus, the bulk pressure that can be applied to a larger object. Let's imagine an object that is immersed in a fluid. That object is going to feel an external pressure squeezing in on all sides from the fluid, whether that is an air pressure or a water pressure. It's going to apply effectively a constant pressure on all sides, all exposed surfaces of the object. You can imagine what's happening here is that we're going to have compression and volume reduction. Imagine if you had an object that we lower into the depths of the ocean. As you go deeper and deeper, the water pressure increases, and that is going to compress the object and make it shrink somewhat. And so the bulk stress, the stress on this large volume of material, is the change in pressure of the object. So the new pressure minus the old pressure. And that bulk stress results in a bulk strain, a fractional change in the object's volume. Whenever we talk about a fractional change, that is the change relative to the original value. That is the change divided by the original value is the fractional change. The bulk modulus, capital B, is the proportionality constant for this compression, and the bulk modulus is a measure of the resistance to compression. As you increase the pressure on the object, it's going to change its volume as a result. Notice that there's a negative sign here, so as the pressure goes up, the volume will tend to go down. The volume will shrink as the increased pressure compresses the object. If the pressure goes down, then a negative change in pressure would result in a positive change in volume. The object could expand if you remove the pressure acting on it. But for a certain amount of change in pressure, if the bulk modulus is larger, that means there will be a smaller change in volume, because a large bulk modulus means that the material is able to withstand that pressure without changing its volume as a result. This is a unitless quantity here because this is volume over volume. Pressure is already measured in pascals, so our bulk modulus must also be measured in pascals. It can also be given in atmospheres. Atmospheres are in SI or imperial, and 1 atmosphere is about 101.3 kilopascals. That is a standard atmosphere at sea level. To visualize what's going on here, imagine we have let's just have a large cube. This cube could be of some material, and it's immersed in a fluid so that there's an external pressure, and that external pressure pushes in on our cube on all sides in all directions with effectively a constant amount. The cube is a little bit larger when it has a original pressure. When we increase the pressure, we get a new compressed volume that is slightly smaller than the original volume. And so our change in pressure is the new pressure minus the original pressure. The change in volume is the new volume minus the original volume. And we take that change in volume and we divide it by the original value to find the fractional change in volume. Liquids are sometimes described by a compressibility K. This is basically the same model, but looking at a liquid in a sealed container. The compressibility is how easily compressed it is. It's the ease of compression, which is the reciprocal of the bulk modulus B, which is the resistance or the difficulty of compression. So the compressibility of a fluid is just the reciprocal of the bulk modulus. If you know the compressibility, you can find the bulk modulus and use the equations we just discussed to find the change in pressure or change in volume of that liquid. Bulk modulus has units of pascals, so the reciprocal of that is a 1 over Pascal or a per Pascal or a per atmosphere in the SI or imperial system.